We take another example to show you how we can use the integrating factor to make an equation exact and to solve it. So I have here given the equation of the curve by the differential equation. I want to find a particular solution, or this will be initial value problem that is passing through the point 2, 1, but we are here told that we have to use method of exact equation. Because look on the equation, we know this is a homogeneous equation. We can apply the method of homogeneous equation also if this is not bounded. If not given here to use the method of exact equation, we can use by homogeneous equation. But here we have seen that because it's written here, so we have to use the exact equation. So I write this one as usual in the differential form. So I can write this equal to solution of this one. So I will write for dx is 2xy. Dx I have to write in my standard form and is equal to x square minus y square into dy. So I can write here this is equal to 2xy dx minus x square minus y square dy is equal to 0. So I need here a plus sign, so I rewrite this one, get 2xy dx, then plus, here we get minus x square minus y square, and into dy is equal to 0. Why I put it here plus? Because we having our formula, our equation is mxy dx plus nxy dy is equal to 0, and there is a big possibility that we may miss this minus sign and our whole of the solution become wrong. So I can write now my mxy is equal to 2xy and my nxy is equal to minus x square minus y square. So this is my equation 1, and I have the m and n. Now I check if it is my exact or not. I take partial m by partial y is equal to 2x and partial n by partial x is equal to minus derivative x square is 2x and derivative y is 0. So we are having here our partial m by partial y is not equal to partial n by partial x. So the equation we are given here, or equation 1, the equation 1 is not exact. So, but we are required to solve it by the method of exact differential equation. We try to get the integrating factor. So to get the integrating factor, in fact in the last example I told you, we get here one we were having y, other way having 3 plus 3x minus y, and we use the both of them because we need only function of y or function of x. So we see that if we use this one, then there is a good possibility that we get the function of x or a function of y. And if we use this one, we don't have to get the possibility because x square minus y square will be not a function of one variable. So I start from m. So I have 1 upon m. We get here partial n by partial x minus partial m by partial y. To remember this formula, always when we start from m, then the partial derivative with respect to n. So we have 1 upon partial m, this is equal to 1 over 2xy, and partial n by partial x is equal to minus 2x and then minus 2x. So we get here this is equal to minus 4x over 2xy. We simplify this one, get minus 2 over y, and this is my function of y. So it means I can find the integrating factor. So I write my integrating factor gy is equal to e to power integral g of y. My g of y is minus 2 over y dy. I can write this equal to minus 2, we take common, and we write here dy over y. I'll get here this equal to minus 2 is outside. E to power minus 2 ln of y. I will get here e to power ln of y to power minus 2. E and ln are cancelled. We get y to power minus 2. This 1 upon y square is my integrating factor. So this is my integrating factor. So what I do, I multiply this equation by the integrating factor to make it exact. Multiplying equation 1 with the integrating factor, we get here 1 upon y square. We get here 2xy into dx. Then we write here minus, I write minus now. This minus, minus plus, minus, plus, and then we are having here minus x square minus y square into dy and this is equal to 0. Multiply by 1 upon y square. We get here 2x over y into dx plus we are having here multiply y square minus x square over y square minus y square over y square into dy, and that's equal to 0. So I get here now my mxy is equal to 2x upon y, and my nxy is equal to minus x square over y square minus plus, we get here 1. Now we check here, again we take the test for this one. Partial m by partial y is equal to 1 upon y. The derivative of 1 upon y is minus 1 upon y square. So get minus 2x over y square. Then we have partial n by partial x. The derivative of this one will be minus, the derivative of x square, y is constant, is minus 2x over y square. And derivative of 1 is 0. So we can see here we have partial m by partial y is equal to partial n by partial x. So I write my this differential equation, this one, equation 2. So I having here the equation 2 is exact differential equation. So we have made this one exact by multiplying by the integrating factor, and it become exact, which means now are we in a position to solve this one. So I am having the value of mxy and I have the value of nxy. I use this one. I having here this side, just take this my equation 3, and this I will take this one as equation 4. So we can write now our using this method, we can write partial f by partial x, partial f by partial x is equal to mxy, this is 2x over y, and then we are having partial f by partial y is equal to, we are having here the value minus x square over y square plus 1. I would like to make the, instead of this one, I will like to make these values as number 1, number 2. This here is my number 3, and this one is my number 4. Now here I am going to start from number 3 and try to find the solution of this one. We integrate both the sides, number 3 with respect to x. So I get here fxy is equal to integral, so get here 2x over y into dx. So when I integrate this one, and then we get here the constant with respect to y, so I get here fxy is equal to x square by 2, y is constant, we take 2 by y common, derivative of x, integral of x is x square by 2, 2 is cancelled with 2, and I left it here x square by y plus gy. So this I put here equation number 5. So we take equation number 5 and we take equation number 4. So I want to find gy. So I substitute the value of partial f by partial y from equation 5 in equation 4. Here I will get the value of partial f by partial y. So partial f by partial y is equal to minus x square over y square plus dg by dy. This is my equation 6. So I take here equation 6 from equation 4 and equation 6. I substitute the value of partial y there. I get minus x square over y square plus dg by dy is equal to minus x square over y square plus 1. Now here we can see immediately is it cancelled, and we are left with this dg by dy is equal to 1. This implies we having integrating both the side, we get here gy is equal to y. So we get here this result, gy equal to y, and we substitute this one in our equation number 5. This is number 7. So from 7, equation 7 and equation 5, I just skip some of this 6. We can write here not 6, number 5, and we can substitute here the value of gy. So I'll get here fxy is equal to x square over y, then plus y instead of gy is equal to constant. See, this is my number 8.